Yep.
Okay. So in Japan, during the 1980s or 60s or whatever, when they were learning to do total quality management and things like that, they came up with something they called the 5 whys. And the idea is if you ask why 5 times, there's nothing magic about 5, but you should get to the root cause of some problem. Okay? For example, let's take the Amtrak derailment. Okay? Why did the train outside of Philadelphia a couple of weeks ago derail? It was going too fast. And it was a curve, going too fast into a curve. Why was it going too fast? Well, I was just reading the paper this morning, and on this page 2, they said he wasn't texting on a cell phone. Okay? He didn't have, he wasn't using a cell phone. But that was something from a week ago, some hypothesis, which apparently they've disproven. Okay? He didn't test positive for drugs. Early on, there was a question of whether someone had dropped a rock, from an overpass, which happens all the time. Teenagers left to go to overpasses and drop rocks on top of speeding cars. And, it killed people and all kinds of things. It's not a smart thing to do. And they build big, in busy areas, they build big fences and stuff to keep the teenagers. Now they have to lob the rocks, okay, overhead. But in any case, if you want to get to the root cause of a problem, you start asking why 5 times. And each time you answer the question, you go to the next question, because each question begs the next question, right? And it actually is not bad. I was actually going to do that the first day, and don't always look at my notes. But I was going to say, why are you taking this course? Because the Navy says so, right? Okay. Why does the Navy say so?
Because they want us to know about steel.
Well, no, that's me. I want to know about steel. They've had welding problems, okay? Why do they want a welding metallurgy course? Because most people think, actually I have a quote in here, that all welding problems can be solved with metallurgy. No, guys, that's not right. And I'll give you some examples of that hopefully later today. But in fact, why do people think that they can solve all welding problems with metallurgy? Because historically, education in this country of welders started big time at Lehigh University in the 1940s. Okay, there were a couple of important people. Bob Stout was the dean of the graduate school. Stout and Doty. Okay, he wrote Weldability of Steels in the 1940s. That was a big place doing welding research. And some of those guys went on out of Lehigh to U.S. Steel, and they developed all the HY steels in the 50s and 60s with Navy money. Okay, those high-strength 7/8 steels, and they had to be weldable because they were going to make submarines out of it. Okay, and then Lehigh didn't really keep their faculty current in that area very well. They did have a guy, Al Pence, who was still around, but he rose up to become provost of the university, and once you get to the administrative levels, no one's really minding the store at the lower levels. And so what happened is, up at Rensselaer Polytechnic, they had a welding program, but a guy came along named Warren Savage. And Doc was a wonderful person. They called him Doc Savage because of the comic books, okay? And Doc was a wonderful person, could have been alcoholic, but he was a wonderful person, and his students loved him. John Lippold was one of his last students, okay? Doc turned out all kinds of welding metallurgists. And because of this legacy of RPI and Lehigh, everybody thought that you solve every problem in the world by metallurgy. And my quote is from Maslow, if the only tool you have is a hammer, you see every problem as a nail, okay? And so you have to be a little bit broader. So if I start asking some of these 5 whys, it's sort of interesting where it leads you, okay? And it's a useful technique. I have gotten up to 7 on some of the whys to get to what I thought was the real major thing. Shaq, we're going to we will have class that, I think, pretty sure we're gonna have class next Friday, and we will have class, turns out, rearranged some of my schedule and stuff, so we will have all the hours next week, and probably Friday, I'll confirm that tomorrow.
Okay, thank you.
But most thing is breakfast, right?
Yeah, it's almost way right now. I'm sorry, everybody. I moved up the delivery time to 7:20, and there's a new person this morning, and she's on her way. So
Okay, well, that's fine.
I try to control.
We got the long day.
And they shot back.
Well, now we know how much.
My fault. Fuck it. My
I don't
fault.
know, now
Sorry.
we know how much influence you have.
Yeah, exactly. Well, that's a lesson I've learned long ago.
He's trying to
The other thing, we need to start scheduling presentations for next week. Okay, and I talked to some people about presentations, we can talk about them again later. But I need to start talking about other things. But first, we're gonna start with an experiment today. Okay? And this is gonna get us into hydrogen diffusion. It turns out the rate at which hydrogen diffuses out of steel is similar to the rate at which carbon dioxide diffuses out of soda. If I make a weld and there's moisture in the air, or cellulose in the electrode, it will be releasing all kinds of hydrogen. See the bubbles in there? Later, in the second hour today, we'll probably watch a video showing you bubbles coming out of steel. But for right now, all I want to do is prime my experiment. You can see the rapid release of bubbles, which would be similar to hydrogen, although this is CO2. And you've seen this before, right? So, good enough. Why don't we shut it off and then, well, actually, why don't we, well, yeah, these things are pretty quick. Go ahead and shut it off and everybody go get this out. Zal asked me about, well, can it be molecular, or does that have to be, or can the hydrogen that does an embrittlement be H2? And the answer is no. If I have moisture in the air, we know it doesn't embrittle steel if it's just humidity in the air. I mean, every piece of steel in the world, there's humidity everywhere. H2O doesn't dissolve into steel. And even if you break it down into hydrogen, as molecular hydrogen, H2, it doesn't go into steel. If you're going to go to lab supplies and order a 2,000 PSI tank of hydrogen, it comes in a steel container. That doesn't, I mean, you wouldn't put it in there if it was going to embrittle it. You then have a bomb, right? What's really bad is if it's atomic hydrogen. Atomic hydrogen is basically just a proton and an electron, and it can dissolve into steel. And we're going to talk about that today. Okay? What's even worse is if you ionize it, and it's just a proton. Protons can go through there like CO2 through water. Okay? At that speed. And we're going to see it. What does a welding arc do? It turns it into protons. You've got a plasma with a bunch of protons in there. Okay? And there's almost nothing we can do about it because those protons are small. I tried to use a broom to sweep them up, but it just doesn't work. Okay? So there's a problem. So, any questions on that? Okay, so we had talked about hardness and hardenability. I'm going to give you more precise definitions. And unfortunately, I have to teach you some more about basic steel metallurgy. But understanding steels, which are 95% of all metals, okay, and this is supposed to be a metallurgy course. Hey, I'm covering this stuff. And some of these principles apply to other metals like aluminum and titanium and stuff. We'll get to those. So even though it seems like I'm spending a lot of time on steel, it's only because it's true. And okay. So hardness we talked about. This is right out of the Metallurgical Dictionary. Hardness is a measure of the resistance of a material to surface indentation or abrasion. Okay, may be thought of as a function of the stress. I told you this stuff. This is sort of a review yesterday. Okay, hardness is actually 3 times the stress in terms of kilograms per square millimeter or whatever units, PSI, whatever you want to use. Required to produce some specified type of deformation, okay, plastic behavior. Okay, I mean, I'm just using different terms for the same thing, okay?
And is that specified type explicitly the top of the curve?
No,
Of
it can be the yield point, it can be the top of the curve, depends on what types of correlation, because hardness is just an empirical thing.
Okay, so that in and of itself seems like we're explaining how you have a difference between 2.8 and 3.2 times the,
Exactly.
right, so,
Are you on the top of the curve, or you're somewhere at the yield point? And, hey, there's scatter in all this, that's another thing I was gonna talk about. Did you know there's scatter in materials? Not every piece of material is exactly the same? Really? Most scientists don't know that, huh?
Yesterday you touched on the Burnell, the Rockwell, and the Vickers.
Yeah, and what are these others?
Yeah.
And where does it get down there? I was gonna cover those, okay. There's no absolute scale for hardness. It's an empirical scale. To express it quantitatively, each type of test is its own scale. Burnell, we talked about, that's the one inch diameter hardened steel ball, a piece of ball bearing, okay? Rockwell, it's just the name of the company that developed this little test that uses either 60 kilograms, 100 kilograms, or 150 kilograms as the load. And it can use either a diamond indenter, a 1/16 of an inch steel ball bearing, or an 1/8 of an inch steel ball bearing. And each one of them is a different scale. They have fancy scale names like A, B, C, D, E, all the way out to like M, okay? Depending on the load, type of indenter, and whatnot. Okay, Vickers, again, Vickers started out with a different type of diamond cut. You know, diamond is complex and you can cut it on different planes. And Vickers uses a different type of cut. Then Knoop, okay, Knoop and Vickers use diamonds, so does Rockwell. Rockwell uses hardened steel balls. These two only use diamonds, but different cuts of the diamond to make a different shape indentation. Okay, we don't have to get into all that. In Schlieroscope, I mentioned, you just take a hardened steel ball and you drop it and measure the rebound. You don't even actually do any indentation. The problem with that is the value you get depends on the stiffness of the thing you're measuring, okay? If you drop it onto a trampoline, it won't bounce very high, folks, okay? So Schlieroscope is, if you need something portable, you can use it, but it's got some problems, okay? So that's hardness. Hardness is a measure of the resistance to surface indentation. Yes?
I'm just really curious, why isn't the definition more pinned down? I mean, so if I were in charge, I feel like I would say, okay, look, it's limited to, you know, the peak of the elastic region on the stress strain curve. That's it, done, and then everyone can agree. Why? I mean,
Well, metallurgists have to have something to argue about. I mean, why? Okay, well, you can get, each measure could be a better measure of what you're trying to get at. This is an indirect measure of what you're really interested in. Like, you're interested in the whole stress strain curve. It turns out, Dr. Belmar, who gives some of these lectures during the school year, has started a company based on his doctoral thesis at MIT, where he was doing fundamental studies of friction rubbing of metal that's against metal. He was scratching things. He did a PhD on scratching metal. Pretty exciting, huh? Well, if you knew his thesis advisor, you would understand. Okay, but it turns out there are, Dr. Belmar is a very practical person, and he is now developing a test where you would scratch the piece of metal and measure the groove, the depth of the scratch, and how the metal rolls up along the side. Like a plow, it's like plowing steel. You measure all that, instead of getting one number, which is the hardness indentation depth, he actually is getting he's not getting the shape of the groove, he's getting the depth of the groove, the force that it takes to plow the groove, the height of the metal that's rolled up on the side, and his intent, and he's done it theoretically, and now he's actually demonstrated, is to get the whole stress strain curve by just doing a scratch test with an instrument scratch machine. And so he's working with all kinds of people down in Houston because the Pipeline Safety Administration of the Department of Transportation has now told the pipeline companies, you got 45,000 miles of pipe buried in the ground for distribution of oil and gas in this country. Much of it was put in the 1940s and 50s. We want you to prove the properties of this stuff that's in the ground. Because they've had some ruptures. And people don't like 50,000 gallons of crude oil in their backyard or in their lake where they drink the water from, okay? So, and people have, you can go to Instron, which sells equipment, mechanical test equipment. For 25 years, they've had fairly good instrumented Rockwell testers. In fact, Instron purchased the Rockwell company. They own it now. And they will sell you for, instead of selling you a Rockwell tester for $10,000, and I have one in the lab, if you guys want to see it. Apparently it's the last one in MIT. Okay? I was surprised. There used to be a dozen in this department, okay? But everybody's doing nano now. We have 4 nano hardness testers on the Infinite Corridor worth a couple $1 million, but there's only one remaining 30-year-old Rockwell hardness tester. They do have instrumented hardness testers that measure the force as it's making the indentation on the old Rockwell test that was developed over 100 years ago. And you can get more information out of it, but you don't get the full stress strain curve, okay? And there's, I mean, for non-destructive testing, there's a lot of people who would like to have that extra information. Now, you know, there are times earlier in my career when I came up with some new technique to inspect some metal. And I remember I was working fairly closely with David Taylor, Annapolis. It's closed now, it's David Taylor Carter-Rock, but that's the Navy's NAVSEA's research laboratory. And I was working with people like Electric Boat. And I remember it came down, talked to Electric Boat and said, I got a new way to test something. And they wanted to throw me out of the shipyard. The last thing they wanted was another test they had to meet. Okay? And there's a lot of truth to that, okay? We need to spend more time coming up with good tests rather than more tests, okay? You can test things forever and you'll never get anything built. It's sort of the critical mass of management. Which actually, that's a good story. You don't really care. I mean, it breaks the train of thought on steel. So back in the early days of the Leaders Global Operations Program, this was 25 years ago. So I went down to United Technologies and to meet with them. And there was a guy who was vice president of manufacturing. And he had been vice president of research at United Technologies. United Technologies, Pratt & Whitney, they were a big research-driven company. But this guy had switched from research to become vice president of operations because, as he said, if this company is going to survive, it's not going to be on research, it's going to be on making things better. Okay? And so he decided he was going to go where the real problems of the company were. And he told the story about the critical mass of management. Okay? Turns out Hitler had a company, had a plant, an underground plant that made ball bearings. And so here's the plant, and he drew this diagram on the board. So here's the factory, and it had a tunnel, and there was a, I've already screwed it up. Let me start it. We need to start lower. So here's the factory, and here's the offices. No, I shouldn't do it like that. Here's the, we'll call it management. So the colonel that was running this factory for the ball bearings had his staff in here, and they would go through the tunnel into the factory, and they were a very productive plant. Well, Hitler had a burned out general from the Russian front, so he decided to send the general to help the colonel, okay, manage this factory. And it turns out they went into the staff office, and it turns out there was a problem because the general staff that he brought with him were always kind of screwing up and going around the colonel's staff. So the colonels decided to build a new office for the general staff. I'll call it General Staff 1, because the story is Hitler had another burned out general, and so he sent them, and so the colonel, having learned his lesson, built another management office, okay, over here, and now his staff could manage the flow of troublemakers coming into the plant, okay. Well, then there were so many troublemakers trying to get into the plant, the colonel's staff couldn't do any work. So he decided he had a solution. He formed a meeting room And he put tunnels there. And this was the critical mass of management, okay? These two general staffs could keep themselves busy and not interfere with production, okay? Well, turns out the Allies found the plant and they bombed it out. And the people in charge sent a message back to Berlin and said, send us some money to rebuild our meeting room so we can get this plant back in operation. Okay. That's the critical mass of management. Okay. So, see, I told you it's a good story. Remember that story because you will encounter it time and time again, okay, in your organization. Okay, so hardenability, on the other hand, instead of hardness, is actually different. It's the relative ability of a ferrous alloy to form martensite. What's martensite? Martensite is a particular crystal structure that is the really hard form that you get when you quench the steel. Okay? Martensite, when quenched from a temperature above the critical, I'll explain what that is in a second. Hardenability is commonly measured as the distance below a quenched surface at which the metal exhibits a specific hardness, like 50 Rockwell C, which is HRC, for example, or a specific percentage of martensite in the microstructure. Okay, what's the upper critical range? Well, the upper critical range is right here on the little iron-carbon phase diagram. And remember, this is gamma iron up here. I don't know that I ever told you that. Gamma iron has a different crystal structure. It's space-centered cubic. This is space-centered cubic. Why do we call it space-centered cubic? Because it's a cube, and it's got an atom in the center of each face. Okay? Face-centered cubic. Like what we call austenitic stainless steel. Gamma iron is also called austenite. Okay? After Robert Austin, who was a British metallurgist in the late 1800s. At low temperatures, the stable form of iron is body-centered cubic, which you got a cube, but instead of an atom on each face, each one of the 6 faces, you got one in the center. Okay? That's BCC. So you have FCC, or gamma, or austenite. Down here you have alpha iron, or BCC, or what we call ferrite. But when you quench this stuff from the high temperature and cool it very rapidly, you won't get exactly this. You'll get another phase, which comes out as little needles. It's called martensite, after Adolf Martens, who was a metallurgist in the late 19th century. Okay, and why do these things are named ferrite and martensite and stuff? Because the first metallurgist, the beginning of metallurgy, was in the 1880s, and a British petrographer, geologist, okay, a guy who polishes rock, decided to try to polish steel. And he looked, and then when he polished it, it was just a mirror. You look in a microscope, it's just a mirror. And then he decided to etch it with some acid. And all of a sudden, he started seeing structure. And he started calling these things ferrite, or sorbite, or martensite. I mean, he didn't call them all these other names. But sorbite's named after Henry Clifton Sorby. He was the first metallurgist, okay, in the 1880s. The metallurgy came to this department, the name, in 1888. And MIT was formed in 1965. This was the geology department, geology and mining, okay? Metallurgy didn't exist in 1865. It wasn't until the 1880s. And Sorby, and these people then started studying all this stuff. That's why I did that term paper I talked about. I went back to the basement of the MIT library, caught a cold that fall, reading these old original papers from the 1890s and stuff, as the metallurgists were trying to figure out what was going on in the structure of the steel. There's also, in addition to hardenability, oh, I didn't tell you what the upper critical temperature is. Yeah, let me get carried away with my stories. So this is temperature versus composition. The upper critical temperature is this one right here. I'll blow it up. Here's the austenite, gamma iron, austenite, and then alpha iron, ferrite, and here is the upper critical temperature. Here at 0.77, carbon is the lowest temperature at which austenite is stable. This is a solvus line for carbon in austenite. This is a solvus line over here for carbon in ferrite. In this region, you have both of them, and this you have to heat up above this line. So if it's very low carbon steel, you got to be above 912 degrees centigrade. If you're high carbon steel, you only have to be above 723. You quench it down, okay? Whatever the slave's body temperature is. If he has a fever, you're not electrified as whatever. You quench it in water, and then it's glass brittle. And what do you have to do? You have to bring it back up to around 400 degrees Fahrenheit, or actually 600 degrees Fahrenheit. Somewhere in the 400 to 600 degree Fahrenheit, or above 1,000 degrees Fahrenheit, like 1,000 to 1,200 degrees Fahrenheit, to temper the steel. Take some of that hardness out of it. You don't want to be Rockwell C60. That's too brittle, too hard and too brittle. Has a strength of 300,000 pounds per square inch, but so brittle that if you hit it very hard with a hammer, it'll shatter. Okay? So you want to get some ductility back, and so you temper it. If you're tempering at a relatively high temperature, like 1,000 or 1,200, that's what we do with HY80. We make a steel that can be tempered at a high temperature so that when it sees the heat of a welding arc, it can tolerate it.
Doesn't tempering release some internal stress in the structure of the metal as well?
Yeah. It turns out.
I always thought that was like the primary reason you temper. Is that not the case?
Well, but relieving that stress, it gets rid of the brittleness.
Okay,
The
so
stress-
it's the same exact. It's the same explanation. For the
Same explanation, just
Okay.
which direction are you coming at to? And it turns out what happens, the carbon, if you did this with absolutely pure iron, you would not form martensite. Steel is an alloy of iron and carbon. The carbon is actually an interstitial small atom that's found in the interstices. There are octahedral sites, okay, 8-sided sites, where the carbon can sit between the larger iron atoms.
So these are all atoms of iron.
These are all atoms of iron.
Okay.
Okay? When you quench it, it wants to transform to this, but it does it in a diffusionless displacive transformation, also called athermal. We're getting into metallurgy you don't need to know. But I mean, metallurgists, we know more about steel than any other material in the world, including silicon. Why? Because we use so much of it. It's such a huge industry, and we've been studying it since 1888. There have been billions and billions of dollars spent on understanding the microstructure of steel. And it's a very rich field. When you start looking at a phase diagram, it's this complex, and you start throwing all these different alloying elements in there, you end up with something that's very, very sophisticated.
So is body-centered or face-centered cubic the stronger metal?
Neither, well, they're both very soft if they have no carbon. If you put carbon in, it will be stronger proportional to the carbon. If you quench it, the carbon because of the displacive, non-isotropic way this thing transforms, the carbon goes into preferential sites, and it will not form body-centered cubic, it forms body-centered tetragonal, because the carbon atoms make one axis a little longer than the other two. And that's the strain, that's the residual stress, if you want to call it that makes it so strong, okay, and difficult to deform. But if you temper it, that carbon moves around and relieves some of that stress, and it starts to revert back to closer to the body-centered cubic.
Okay, so quenching it in a way, it's almost like, I'm thinking like your old like Greek aqueduct arches, you know, like you have a compressive stress that helps hold it together.
Right.
So here, when you quench it, it's kind of like creating all this internal stress that makes it much, much more harder because of the structure of each
And more
atom.
brittle. Okay. Unacceptably brittle. Okay. No one uses
Then why quench
untempered
it?
steel.
Why quench it in the first place? To maintain the...
Because you have to get the strength. This BCC has a strength of 35,000 psi. Until you quench it, heat it up and quench it. Now it's got 10 times the strength, 300,000 psi.
But it's both body-centered cubic.
Well, it's not, the martensite's not exactly, it's body-centered tetragonal,
Okay.
and to a, you know, a PhD metallurgist, that's very important in understanding the details. You don't need to know that detail. It won't be on the quiz.
I understand.
Okay.
Seems relevant.
Okay. I mean, there are people who spend their lives studying this. Morris Cohen, okay, who was this professor here, spent his life studying martensite. He was kind of Mr. Martensite. Okay. Anyway, so that's the difference between hardness and hardenability. And yeah, I know you guys get tired of steel, but we won't be doing it forever. Okay. I talked to you about, well, there's this problem that if the only tool you have is a hammer, you see every problem is a nail. And I talked to you about some things like hot cracking. Solidification cracking or hot cracking is because we have to have the manganese in there to type the sulfur, or otherwise we get this slurpy type of structure when it's up near the melting point, and it just pulls itself apart as it contracts, as the temperature comes down. Okay, it contracts due to thermal expansion, thermal contraction. Porosity, well, we get gases in there. Porosity is not usually a huge problem unless it gets really gross, like 10% by volume, and then it weakens the steel. Hydrogen cracking, we're going to spend a lot of time on. Lamellar tearing. Lamellar tearing was a problem back when we had steels that had 400 parts per million sulfur and big oxide inclusions. This was the steel making technology of the 1960s and before. Big problem. When I worked at Bethlehem Steel in the mid-70s, the oil companies were building a lot of big offshore oil platforms. They were big, heavy steel plates, 3 and 4 inches thick. They were getting lamellar tearing problems because the steel wasn't very clean. Well, the Japanese taught us that you can make clean steel inexpensively if you have modern facilities. Okay, but not if you have 1911 blast furnaces. Okay, like Bethlehem Steel had. Okay, and so the United States fell behind, but lamellar tearing is not a problem today. Instead of 400 parts per million sulfur, it's easy to buy steel at 50 parts per million sulfur, and you don't get lamellar tearing. But my office mate at Bethlehem Steel, that was one of his projects, was lamellar tearing. Okay, I think I said I don't know that I've ever seen more than one problem in the real world of lamellar tearing. Although 40 years ago, it's a big problem, but not today. Okay, so. But the metallurgists, you know, the metallurgists are going to tell you about it because this is part of their history. But it's not necessarily part of their problem set today. Reheat cracking. Well, my supervisor at Bethlehem Steel had done his doctoral thesis at Lehigh on reheat cracking of steels. Turns out if you stress relieve a steel, we take steels and we put them in a furnace at 1200 degrees Fahrenheit for an hour to get rid of the residual stresses from welding. And it turns out sometimes they would come out and they actually hear a pow inside the furnace, and it was a great big crack going through your steel. And you'd have this very intergranular crack. Well, it turns out it was small amounts of sulfur again, arsenic, phosphorus, antimony. Shouldn't have any bismuth in the steel, but that would do it. That's what Carl Meissner did his doctoral thesis on. He was one of the last of the line of the great metallurgists at Lehigh University, welding metallurgists at Lehigh University. Okay, he was my supervisor at Bethlehem Steel. Okay, we learned how to solve the reheat cracking problem. It was a problem all the way up through the 1970s, but it's not really a problem today. Okay, solidification cracking. We talked about the low melting sulfur compounds. You put manganese in there. Now, when we get to stainless steels, we're going to find some other problems. And you get to aluminum alloys, you're going to find lots of solidification cracking. Low heat affected zone toughness due to grain growth. Okay, let's talk about that for a second. Okay, here's my HY80 weld from 30 years ago, made electric weld. And you can see the heat affected zone. See this little black region next to the fusion line? Okay. Well, let's go back to the history of that Navy report from 1946 about the Liberty ships. What they found, if I read the conclusions to you, they found that the ships that sustained the big cracks in the hull structure had less than 10 foot-pounds of Sharpie toughness. What's Sharpie toughness? A bar Sharpie bar. A Sharpie test has been around for 105 years. 5 years ago, they celebrated the 100th anniversary. A Sharpie bar, how many people have seen a Sharpie bar? One.
Is that the V-notch?
Yeah, it's the V-notch, okay. So it's 1 centimeter, it's a French test, Sharpie, C-H-A-R-P-Y. He was a French metallurgist of 105 years ago. And it's the pneumetric, so it's 1 centimeter by 1 centimeter by 10 centimeters, and it has a 2 millimeter notch right there, okay, in the center. This is like carrying the piece of paper, okay? You put a notch in it, and the bottom of that notch is, the best way to do it is to broach it, okay? Run a cutter through there, because it has very specific requirements on how sharp that notch should be, so that you get the same amount of stress at the tip. It's a stress concentration. And you put it in a big pendulum machine, and you raise this 100-pound weight up on this arm, and you put the Sharpie bar in there, and you let the pendulum go by gravity, and it swings down, it breaks the Sharpie, it hits the Sharpie back here, call it the tuck, which is the hammerhead. So a big piece of steel hits this thing, and it breaks it and goes flying off. If you've ever been in a room where they're testing Sharpies, they got little screens to catch the shrapnel. Okay, it doesn't go that far. And when I was at Bethlehem Steel, we had a 264 foot-pound Sharpie machine. That's about, let's see, it's 0.75 foot-pounds per joule of energy. Foot-pounds is a measure of energy, okay? Remember, toughness is a measure of the energy of fracture. Tensile stress is a measure of the force of fracture. This is not really a toughness measurement, but it is an energy measurement that people have tried for years to relate to fracture toughness. And there are correlations, okay? We actually have fancier, more expensive tests today. Each one of those little Sharpie bars cost $100, roughly, when I was at Bethlehem Steel. And usually, because they're scattered, you usually have to test 3 at any given temperature. If you want the full Sharpie curve with temperature, you might have to have 15 to do 5 different temperatures, or 5 different sets of 3. And we learned, because we had a machine shop up at research labs, but we had to get our Sharpie bars, because of company rules, machined down at a regular big machine shop at the steel plant, because they were doing these bars all the time for test plates and stuff. And we learned that you would call up the foreman down there and say, "Are you busy?" And if he said yes, you would send it to him. If he says no, he didn't have a lot of work, you would wait, because you didn't want to pay $150 for a Sharpie bar. If he was really busy, you might get him for $75 a piece, okay? And if the guys are just starving it, he just wanted to fill up his order book, right? So we learned to do that. There's a lesson in that story. Okay, so in any case, so the Navy in 1946 found out that, you need the ships that sustained brittle fracture had less than 10 foot-pounds. And the lowest I've ever seen in my career is 2 foot-pounds, the most brittle steel I've ever seen. Typically 5 foot-pounds or less is extremely brittle steel. And I actually meant to bring Don Satterway, a faculty member of this department, sent me a link to a problem they're having on the Oakland Bay Bridge. Okay, they have some big steel tie rods right now, and they're corroding, and they're breaking, and they're holding this bridge up. It's a multi-billion-dollar bridge, right? And turns out we don't have to get to. I mean, we can get to it, or maybe I'll find the email in the break. But it's hydrogen cracking, because it doesn't show up right away. It takes a few days to show up. Okay, and it's due to corrosion. Another way to get your hydrogen into the steel is not just a welding arc plasma. It can be by a corrosion process. You can take a bolt that has no welds, stick it in seawater, put a stress on it, and the bolt will crack in a couple weeks because of hydrogen cracking. Okay, So it's not just welding, it's lots of other things. One of steel's Achilles heels is hydrogen embrittlement, but other materials have hydrogen embrittlement. In any case, what happened with these Sharpie tests? Well, in the 1950s, the Navy said, okay, after the report came out in 46, took a while to digest it, and they said, okay, we're going to require 15 foot-pounds. We're not just going to require a tensile test on our steel. We're going to require 15 foot-pounds of Sharpie energy. And we're going to require it at the weld because a lot of these things are found in weld defects. Okay, so base metal, weld fusion line, weld metal, we're going to look everywhere we can. Well, then the Coast Guard comes along in 1960. Hey, for the Coast Guard. Coast Guard wants to be safer than the Navy, so they decide if 10 foot-pounds was the problem level, and the Navy wanted 15, well, the Coast Guard would ask for 20 foot-pounds. Okay? And turns out, if the Navy was going to look at the weld, in the weld metal, so they take a Sharpie specimen right here at the fusion line, and over here in the base metal. Okay, that's what the Navy would do. Remember, each one of these is $300. Okay, with the testing. Like $1,000 worth of testing to do this. Well, the Coast Guard decided, well, we're going to be carrying liquefied natural gases on some of these ships, and we want to be extra safe, so we'll require it at the 1 millimeter position, the 3 millimeter position, and the 5 millimeter position, and the base metal. Okay? And you got to meet not 15 foot-pounds, but we're going to be even safer at 20 foot-pounds. So when I was working on the skirts to hold up these big aluminum tanks for the LNG tankers down here at Quincy, they're building Quincy, that's what I had to do. Okay? I had to measure each one of those locations along the weld. I had to weld a plate a foot long just to get all the specimens out of it, because you had good tensile specimens and everything else. Now, guess what the shipyard did? This was a big problem. Even more tests that had to be done. That's the last thing they wanted to know, is they had to pass more qualification tests, right? Well, it turns out there was variability in the steel plate, and it turns out Bethlehem Steel, at that time, the base metal would meet 20 foot-pounds 70% of the time when it came out of the mill, first pass. Well, you didn't want to scrap 30% of your steel, so what would they do? They would send it back through the heat treatment furnace. In this case, it's a normalization furnace, where you just heat it up to upper critical and you slowly cool it without a bunch of, and you get a finer grain size, and it should give you better toughness. So they would do a reheat or normalization heat treatment, okay, to try to improve the toughness. And after they did that, maybe 2/3 of the ones that didn't pass the last time, 8, 18, or 19, would now pass at 20 or 21 or 22 or whatever. And then some of those that didn't pass, the 10% that still didn't pass, they would put through a second renormalization and see if they could get it to pass, and some of those would pass, some of them wouldn't. They'd scrap the ones that, after 3 tries, that didn't know. How many times are you going to put it through there, okay? Now, if they were Japanese, they would just lower the sulfur, okay? But not, you know, it was going to cost us money to do that, so we didn't want to do it. But every now and then, the shipyard would get a report from Sparrows Point that this plate, this particular plate, had 30 foot-pounds of toughness, okay? A really good steel could stop the hammer at 264 foot-pounds. Okay? When I was developing my steel, I used to stop the hammer on a regular basis. Okay? If you stop the hammer, you have to recalibrate with about $2,000 worth of Sharpie bars that you used to buy from Watertown Arsenal, which is a mall now out here in Watertown, Massachusetts. Now you buy it, I think NIST, National Institute of Standards and Technologies, sells it as they sell standard Sharpie bars that are supposed to be calibrated. But anyway, but you can stop at 264. So the steel could be 264, or it could be 5 foot-pounds, or it could be 15, or it could be 20, or it could be 30. Well, what did Quincy Shipyard do with that 30 foot-pound plate? Nope, they turned it into test plates. Because what are you going to test in the laboratory? You're going to weld this huge plate, right? That's going to be part of the ship, but you got to have a piece to test. So you take 2 little pieces of steel about this size, you put them on the end of the weld, and you weld a tab, a 1 foot tab of test plate on the end of the
They
thing.
welded good metal on other sheets.
No, they took the other sheets that were coming from Sparrows Point that averaged 20.5 foot-pounds on average. 20 was the minimum. They were measuring 20.5. When they found one outlier at 30, they would cut all their test plates out of the 30 foot-pound plate, and that's what they sent to the lab to meet all these properties. Okay? So, Mr. Coast Guard, what do you think of that?
That's not too good.
Okay. Now, this story tells you there's always a way to get around. Okay?
That much we know.
Yeah, well, this is your job in the future.
I'm just impressed that they weren't just writing 20 instead of steal off regardless of
If you want,
There
I'll give you the name of the test lab down south of Boston. And if you have to test concrete cores, no need to send the core in from the shop. They'll just send you the test report. All right, good. Yes, it's criminal, okay? We'll try to prove it. Actually, you could if you had subpoena power and things like that. But there are labs that do that, yes. And you probably said that because you know of situations where that's been done. Falsifying test reports, right?
You can either confirm or deny.
And now we find out why some people in the shipyards and the ship don't always get along. I don't know. Okay, so variability in steels. The steel companies know a lot about the variability of their steels. It used to be, this is Contribution to the Metallurgy of Steel. This is published by the American Iron and Steel Institute. This one is September 1974. The variation of product analysis and tensile properties, carbon steel plates, and wide flange shapes. Wide flange shapes are like I-beams and stuff. And in the old days, this is actually the June 1984 issue, but this is wonderful reading. Graphs, tables, and it actually will give you the variability of hundreds, if not thousands, or tens of thousands. This steel company, the Central Machine Shop at Bethlehem Steel, was turning out Sharpie tests on plates. They had all the data. Well, every now and then, in an anonymous way, the steel companies would give the data to the American Iron and Steel Institute, and they would give the sort of the sanitized version of variability. Okay? So we have, well, here's some of the variability. Okay, lateral expansion is related to foot-pounds, and you can see the variability from 16 to 71. Okay, well, here's absorbed energy in foot-pounds. 16 to 61. Okay, pretty wide range. Oh, but this is a good plate. Look at this. All the way up to 26 from, actually, 2.94, not 0, but 2. I mean, don't buy that steel, baby. Okay. So there's data on this variability, okay? And there's data on the composition. And I'll tell you the story of the composition. So here we have a piece of steel pipe, which, I don't know if you're going to be able to see this. We cut through it because it has, I'll just pass it around. But first I'll show you, there's a big missing piece here, okay? This is seamless steel pipe. It's been painted on the outside. It was buried in the Gulf of Mexico. It was to carry oil, hey Coast Guard guy, okay, from a production platform to a on shore, right? This never carried any oil in it because what happened is the steel mill that made it, which will remain nameless, but it's in northeast Ohio and it's been there for 100 years, okay, but it's no longer named. Young's found sheet too, but it will remain nameless, okay? They produced a piece of steel and sold it, and they shipped it down to Houston to be used in building this pipeline under the ocean, or laying on top of the floor of the ocean. And before it left the steel mill, it had to go through a full ultrasonic inspection. It had to go through a pressure test, a hydrostatic test. They have like 75% of its yield strength value. So that's we actually call it a proof load test. Every length of pipe. This is seamless pipe, no welds in it. They basically take a piece of hot steel at 2200 degrees Fahrenheit and they have a steel mandrel that's cold, and they just shove it through there, 40 feet long. And they take a solid piece of steel and turn it into a big red piece of hot steel pipe. And it can be heat treated and other things afterwards. So that's steel tubing. They had pressure tested it, done a proof load test to show it would hold the pressure. They took it down, they sandblasted it, took off all the identification markings, painted it for corrosion resistance. That's a very good paint on there, by the way. Laid it in the bottom of on the seabed, and did one final pressure test after it had all been welded together, laid on the seabed, and it failed. And when they cost them $5 million to go retrieve it, because it's on the bottom of the seabed, these supply ships and maintenance ships and diving ships might cost $100,000 a day. Okay, they're not cheap. Anyway, they recovered it, sent it to me to look at, and what had happened is, what most likely happened is one of those mandrels that goes pushing through this piece of hot steel, finally, after multiple uses, had developed a fatigue crack and spalled off a piece that got rolled into the surface. And it passed the first two tests, because in the first two tests, we had a piece of embedded steel that was plugging the hole. But over time, that piece of embedded steel, basically the core bond, broke loose, and on the third pressure test, it leaked, and they had cost them $5 million to replace
So
it.
this was not the failure point, but it's an example of why the pipe.
No, that was the failure point.
So did this break through on, like, right here where you also notched it?
No, well, we thought that was the best location, so we cut it out. We cut it out to do metallography on it to see what we could see, and we saw that it was decarburized there, so we knew we lost some carbon. We knew that surface was present at the steel mill. The steel company had two defenses. Well, there's nothing wrong with the pipe. Well, that's kind of not a very good defense. And the second defense is it's not our pipe. You have no identification. You took all the identification off. You bought steel from other people, and it must have been one of their pipes. So it turns out, even though it's got carbon, manganese, sulfur, silicon, phosphorus, sulfur, it also has residual small amounts, unintentional amounts of nickel, might be 0.15% nickel, it could have 0.08% copper, okay, it has a couple of other things. Let's say it has 10 different elements. I can go to this thing, which gives me the composition variation of various steels. And so if I know the statistical variation of the composition that's produced on thousands of feet of steel, and I do a chemical analysis on that piece of steel, I can then do a statistics to see
It's a fingerprint.
it's a fingerprint. And if I have a 90% confidence level, statistically, that it meets the carbon requirement, okay, typically, and these are narrower ranges than the requirements that you have in the specifications. I'm looking at a specific number. If I measure that it's only a 10% probability that it's not the same piece of steel, times 10% for manganese, times 10% for silicon, I proved that was that same piece of steel produced by that steel company with a probability of 1 part in 100 million. How about that? They weren't expecting that when they said, it's not our steel. Okay, well, you're right. There's a 1 chance in 100 million it's not your piece of steel. So you can fingerprint the steel. I get to do that about once every 2 years in something, okay? Because that's a standard defense. Oh, it's not my steel. Maybe a piece of junk, you're right. Okay? Although that was one of my first jobs at Bethlehem Steel. They had a steel plate that had terrible toughness, And all I got was a small little piece. It was part of a highway bridge on the interstate highway system that had just been built. And I just got one little piece, and we measured the composition, and it was something that was called weathering steel. And it had small amounts of intentional nickel and copper and chromium. But Bethlehem Steel used nickel and copper for its corrosion resistance, and U.S. Steel used chromium and nickel with no copper. Just differences between the steel companies. And so the company that had used it and had this big expensive repair on this bridge sent it back to Bethlehem and said, "Your steel is junk." And I analyzed it and I wrote back and I said, wrote the letter report up to had to go to my boss's boss. And I wrote, yes, you're right, it is junk. It's got chromium in it. Go talk to U.S. Steel. Okay. So there are lots of ways to fingerprint things. I didn't have to go through statistics there. You know, Bethlehem didn't sell that grade of steel with chromium in it. That was U.S. Steel. So you can often tell who the manufacturer is. You can actually sometimes get down to a specific lot of steel by going back to the fingerprint. If you're in the aerospace business, they keep all those records. In the medical business, they keep all those records. Everything is certified. Or the nuclear energy business. Keep all those certifications all the way back, okay? And so they can, if they have a problem, they have to have a product recall. We had a product recall, actually it wasn't a product recall, but there was a problem with a piece of quenched and tempered plate, 100 KSI steel, like HY100, but it wasn't, it was a lower chemistry because it wasn't quite as thick. It was a bridge steel in it. So I was reading about it in the Bethlehem Steel report, and I don't remember if it was Bethlehem Steel plate or if it's just a problem that the Federal Highway Administration had. But the Sharpie toughness was like 5 foot-pounds. It was terrible. And I didn't understand this, and so I was asking this Bob Summers, who's a grand old man of welding. He was a Lehigh grad at Bethlehem Steel. He was one of our grand old men of welding. I said, "Bob, how can this steel be so bad?" He said, "Well, scuttlebutt is they got through the mill without tempering it. It had 160 KSI strength, and it was glass brittle because they hadn't bothered to temper it. It slipped through the process without getting tempered." Okay. You've had that happen?
We've taken some fasteners, non-versatile fasteners, failed in service. They were very surprised they had failed. So my job was to go quality assurance. So all the paper trail. And sure enough, these fasteners were indeed tied to paperwork that said all of this was done. In the manufacturer, and said that no, this is entirely compliant. And then we chased their paperwork they got from their company, right? Because looking at the steel, and so they used for their evidence the properties of the actual roll of the steel and the metallurgy. Well, then we noticed that their paperwork said it has the following properties if heat treated.
Mm-hmm. Yeah.
It was never heat treated. They assumed it was. They machined it, manufactured it, produced it, and produced paperwork with their company logo on it saying it's qualified to these standards.
Yep.
And there's many reasons why that never should have made it that far. They're supposed to destructively test, a certain percentage. It never should have made as far as it did. Sure enough, all through a couple of our submarines, through the bucket systems, were a bunch of these fasteners that were never treated.
Not good news. But these things happen, okay?
Yeah.
That's why you guys are out there.
Yeah.
Keep them from happening. If it happens on your watch, you start looking for a new job. Okay. Okay, why don't we take a break for a little bit?
What's that?